Alright, so today we are going to be talking about the universal approximation of functions on sets. This is going to be by Edward Wagstaff, Fabian Fuchs, Martin Engelk, Michael Osborne, and Igmar Posner. Alright, so what is this paper about? Now this is a really well-named paper, because the title is exactly what it's about. So what we're going to be doing is talking about the requirements that you actually need to achieve universal approximation on sets, and we want to universally approximate functions. So what we're going to be doing is we are going to be modeling functions on sets. Specifically, we're going to be modeling permutation invariant functions. We really don't care about any other kind of functions. And we're going to be using deep sets, where deep sets is a popular method to be a universal approximator on set functions. We are going to be talking about what exactly do you need whenever you're building a machine learning paradigm in order to create these permutationally invariant representations of these functions, or approximations I should say, as it says right here. And I think the best thing we can do is just to jump right into it. So the best thing we can do is define what a set is. That's going to be important if that's what we're going to be talking about the whole time. So a set is a collection of things with no intrinsic ordering. Some examples they give are a point cloud from a LiDAR sensor, a group of atoms in a molecule, or a collection of objects appearing in an image. So a set is pretty much just a group of things. We can think of it as a graph with no edges. It's all nodes. So the first thing that we're going to want to do is talk about deep sets. Deep sets is the tool we're going to be using throughout the entire paper. So what is deep sets? Well, in order to introduce deep sets, we need to talk about Genoese pooling. Let's scroll down. Here we go. Genoese pooling. So let's define Genoese pooling. Genoese pooling is going to be, oh wait, there's a better image. Here we go. Here is an image of Genoese pooling. We are going to take our inputs. Here is an input set. And what we're going to be doing is we are going to be just taking every single possible permutation of this set. And then we are going to pass it through this permutation sensitive function phi. And we're just going to pass every possible ordering of this set through phi. Then we're going to aggregate them, and that's going to be our latent space right here, this aggregation. And then we're going to pass it through a function rho in order to get our output. The heart of what we're doing is going to be on this left side for right now, for Genoese pooling. Let's see, here is a good example. Whenever we apply Genoese pooling, what we're going to be able to do is take our permutation sensitive input, our permutation sensitive phi, and we're going to make it permutation invariant. Now we really don't care about anything that's not permutation invariant. If you have a set and a permutation sensitive function, it's going to change based on how you order the set. But whenever you're dealing with like LiDAR data or something like that, you don't care what order you get the points. You only care that the points are correctly mapped out to what they are. So we're not going to care about things that are permutationally sensitive. We're also not going to care about things that are permutationally equivariant. Equivariant is just the idea that whenever you change the input, you change the output by the same way you change the input. So if you change 1, 2, 3 into 3, 2, 1, you get out, if the function does literally nothing but it's equivariant, you get out 3, 2, 1 instead of 1, 2, 3. But with a permutationally invariant function, it doesn't matter what order you put it in, you're always going to get the same output. So the permutation invariance comes from us taking this set, taking every permutation, and literally just brute forcing our way into this latent space by taking every single possible permutation sensitive function and just taking every single possibility. The problem with this is that it's very hard to do. For a set that's size 5, not a big deal, but a point cloud or a molecule with a few million things inside of it, then, your hands are going to start to shake. You're going to start to worry, is this computationally feasible? So there's a few things that you can do in order to try to make it computationally feasible, such as limiting the number of elements in permutations. So we can think of it, so this is a great image that I'm going to come back to here in just a second. So we can think of it as saying, hey, this is going to be something called k-array-Genosi pooling. We think of it as saying, hey, we probably don't need to plug in the whole set, just a subset should do. So we are going to take a permutation, or here it's the size of the permutation for just standardization, and we're going to take a permutation of m things. The m is going to be the size of the set, and we're going to take k examples from inside of that. And we're only going to plug in the set x of size k and every permutation of that within our phi, within our permutationally sensitive function. We're going to aggregate it over the size of the possible set, and then we're going to have our permutationally invariant output, where, of course, permutation is defined as permutation. And that's great. So let's talk about just a few notable examples of k-array-Genosi pooling. First of all, let's start from the right side. First of all, we're going to have deep sets over here. Let's move to the right side first, because I want to finish with deep sets. We're going to have Genosi pooling with k equals 2. Here we have a set size of 3, and we take all permutations where k equals 2. Right here, we can see, and we plug those directly into our phi. And whenever we do that, we aggregate it, and we pump it through our row. Our row doesn't need to be permutationally invariant. It can actually be permutationally sensitive, but because its input is always permutationally invariant, its output is always going to be permutationally invariant. So if we take that, we can see that we have every single relationship here between the two things. And these, the phi's, are going to take them and put them into the latent space and explicitly say the distance between them, or in a latent space, we can talk about the meaningful relationship between them. So the example that they give in the paper is going to be like ingredients. So like if we think about vanilla or garlic, they really don't taste great together. If we think of it to where like on the left side, whenever we have k equals 1 and you just have to take each individual thing and plug it into the phi, this decoder here is going to have to completely learn that relationship. It's going to have to completely learn all on its own the taste of garlic and vanilla, and that they don't go together. However, with k equals 2, that's going to be intrinsic in the latent space itself. Rho is not going to have to learn that from scratch. It's already going to have a lot of the information built in. So k equals 2 is much more powerful than k equals 1. And from k equals 2, we're going to immediately see the relationship between self-attention, the self-attention mechanism seen in transformers. So if you look, the self-attention is only a slight variation where you take one node and you take every k equals 2 relationship with that singular node. And if you look, whenever you actually plug it into your phi here, you're only plugging 4 things into the phi. Of course, with an attention mechanism, you're going to move from one to the next, to the next, to the next, to the next, so it's not as easy as it immediately looks. But this is a really smart way to have k equals 2 Genosi pooling in a computationally efficient manner. And that's where we get the attention mechanism from. Hey, it's super popular. We've all heard of it for a reason. So this right here, this Genosi pooling with k equals 1, is going to be the most basic form of Genosi pooling. It's also going to be named deep sets. Deep sets actually, there are 3 papers here. There's the deep sets paper, there's the Genosi pooling paper, and then there's this paper right here. This deep sets paper actually came out first, and then they built Genosi pooling as a more general framework for deep sets. So that's pretty cool. We're going to be dealing only with deep sets because it's the simplest case, and if you're dealing with the simplest case, if you prove something, of course it's going to work for k equals 2. It's not even a question. So now that we've defined what deep sets are, let's move on and get into universal function representation. Now, universal function representation was actually proven in the deep sets paper itself. So we're going to go through some notation, then we're just going to talk about what the deep sets paper actually did. Oh, hold on. So what did the deep sets paper actually do? So let's go through some notation first. The set X, which is a bold-faced subscript indexed object. Wait, no, it's not. It has subscript index. So the inputs in boldface are going to be a set. And here is the set X, and X has elements x1 going to xm. Notation 2 says the variable m is always the number of elements in the input set. Notation 3 simply says that we have permutations pi, and this singular permutation pi is going to be a member of all possible permutations S sub m. And we can think of these permutations as a bijection from 1 to m onto itself. On 4, we're going to have f of x is going to be permutationally invariant if the function doesn't care which permutation you use. You can use any from the set S, and what you're going to get out is the exact same thing as if you chose a different permutation from set S sub m. And yes, for all pi as members of S sub m. We say that f is sum decomposable if the function fits in this form right here. If it fits in this form right here, you've done it. You've represented that function in terms of sum decomposition. Proving this, and the requirements for it is going to be the main idea behind this whole section, behind the whole of section 3. So, let's move on. We can talk about the latent space, which is going to be big phi on x. Do you see how this is a set x and not an individual x? The set x applied on the latent space can be thought of as the aggregation of the little phi's on each individual element of x. Now, this is k equals 1 Genoese pooling. This is deep sets. Do you see? Genoese pooling with k equals 1. Deep sets. There we go. I'm not just making this up. So, with this, we can talk about the functions in terms of this row, this decoder, acting on this latent space, big phi on x, which I'm pretty much just going to call phi. Little phi is, well, I'm going to call it that. So, as we move on, we can write z for the domain of rho and the codomain of little phi, and we can talk about that as the latent space, and we can talk about latent space sum decomposition because of it. So we say that it's sum decomposable if it has a sum decomposition whose latent space is z. A little bit long-winded there, but I think it's straightforward. Yeah, oh, we're also going to have the power set of x, which is represented by 2 to the power of x. So let's jump right into it. Now, what did they do in the deep sets paper, Zahir et al. 2017? So there's going to be 2 cases. There's going to be the countable case, which we're going to prove extraordinarily quickly. We're just going to fly straight through it, and we're going to talk about the unrealistic case whenever we have some f of some function which maps the power set of the universe to the real numbers, where the universe is countable. This just means it scales linearly with the natural numbers. So, we can say even that f is sum decomposable via the real numbers themselves. So, because, here's the proof right here, because the universe is countable, x as a member of the universe can be mapped to a unique element in the natural numbers by some bijective function c, where c maps u to the natural numbers. Pretty straightforward. So we can choose some phi so that the latent space is invertible, and we just choose some rho so that the function applied to this latent space gives us everything that we need for the sum decomposition. And if we have the sum decomposition, then it is sum decomposable via the real numbers. We've done it. Now, we can consider some phi of x such that it's defined as 4 to the negative c of x. This looks really arbitrary, but if you look at the deep sets paper, they explain why they want to do this, the main reasons, all that. So, each set corresponds to a unique real number, and that real number r that it corresponds to is defined as the latent space of, if you look at those coordinates at x, that set x. This can be decoded by the set x by looking at the base 4 expansion, and if you just take the inverse of it as a member of the universe, it belongs to x only if the nth dimension of the digit is 1. So, if you get an r equals 1, that means you've nailed it, you got it, you found the correct sum decomposition, you did it. This shows that this latent space is always going to be invertible, and that's it. So for the uncountable case, which is much more realistic, we're going to consider the m element set from the universe, which is a line segment from 0 to 1. So let's jump right into it. Theorem 12. Here is the uncountable universe. So this is going to be a lot harder to prove, so we're just not going to do it. Super simple. The deep sets paper does it, and this paper doesn't do it, and, well, I'm not reviewing the deep sets paper, so if the authors of this paper didn't find it so important, I mean, how can I refuse to believe the same thing? There we go. So we are going to let M be a member of the natural numbers and let F be some hypercube mapped to the real numbers. And we are going to let this F be a continuous and permutation invariant function. This continuous should jump out at you right now. This continuous is a little bit strange, but it's going to come up in just a minute of why we require that everything that we do is going to be continuous. So we say that F is continuously sum decomposable via sum r to the power of m plus 1. So what they do, in order to prove this, the proof is much more involved than for Theorem 11. So we're just going to talk about it briefly. So we map this latent space, which is in some hypercube, to the real numbers of dimensionality m plus 1 defined by this latent space sub q on the set x is going to be equal to this function right here. Now, this should look a lot like what we've seen for the latent space, except for one thing. Do you see this q right here? We don't have a phi anymore. We have an explicit q, and this q is literally just going to be a member of the natural numbers up to m. So it's just going to be 0, 1, 2, 3, 4, blah, 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 blah. So what we're doing is we're just explicitly defining what this phi needs to be. So we show that phi has a continuous inverse. We define this row. Oh no, I was wrong. It's not a natural number, it's a real number. It says it right there. So it's going to map the real numbers of dimensionality m plus 1 to the real numbers by this inverse function right here, because, you know, if you show that your latent space has an inverse, why don't you use it? And we are going to define our phi of x. This is an individual object on x, of course, not the set x, as mapping a real number to the dimensionality of r to the m plus 1 by some phi sub q is defined as literally x to the exponent q. Real straightforward. And it works extremely well. So, after showing that, we can talk about what this paper does. What are we trying to achieve? So, we argue that the guarantee of some decomposability via the real numbers given by Theorem 11 does not hold in practice. Shocker, I know, a toy universe is not the real universe that we live in right now, that we're trying to do machine learning on. The mappings are highly discontinuous. It's discontinuous, and it cannot be computed. From there, we're going to go a step further, and we are going to talk about the guarantee of some decomposability via r to the m plus 1, and we're going to say, DeepSets said it needs to be m plus 1, but we're actually going to come through, and we're going to show that it just needs to be m. It doesn't need to be m plus 1, just m. However, if you go beneath that, if you drop beneath m, universality is lost. You cannot universally represent these functions. And we're going to go a step further. If you notice, the very attentive viewer will notice that this paper is the approximation, not the representation. We're going to prove that you need at least m for the representation, and you need at least m for the approximation for the universal approximation of functions. So now we can jump into why continuity is important. They give just a small example here. We're just going to be, we're going to have some set of images. These images are going to be 256 by 256 pixel images in 8-bit grayscale. And we're going to denote each image I. Oh, it's the domain of them. The domain is I, the set of images I. So there's going to be an element of I. We are going to consider, oh, by the way, we are going to only consider interesting images. We can just consider these to be the natural images of C, which doesn't really matter. It doesn't really play a role in this. So 256 by 256 pixel images in 8-bit grayscale, that's a relatively large number. And considering all natural images, that's an alright size, right? That's a good size. So we're going to consider the 2 to the 2 to the 16th image. This is going to be a funny eye. I have never seen this kind of eye before in my life. I don't even know if it's an I. It might be a backwards J. Who knows? It's going to be defined as just some c to the -1 of this one right here. And based on what we said, if it's the number 1, that means we've got a hit. That means that we've found it and we can say it is in the set. However, if we never get a 1, we can say it's not in the set. However, oh, and it says this is going to be in our set X. However, whenever we try to break this down, whenever we try to say, hey, this is in the set, or hey, this isn't in the set, the presence or absence of the image I in the set X will affect the value of R by 1 point in 4 to the 2 to the 2 to the 16th. That is a very, very large number. We're not even dealing with very large numbers anymore. So it goes without even saying. Well, I'm going to say it, but it does go without saying too. Any decoder row on real hardware will not be able to do this. You would need a bit of time. The essential problem here is going to be the extreme degree of discontinuity. It was the discontinuity that made our search space just absolutely enormous. It was way too big to even go through. So we're going to cut this down. We're going to cut the search space down by only considering functions which are continuous. This is a really, really common thing to do, actually, to only allow continuous functions. This is also going to be in the function approximation properties of the Universal Approximation Theorem from Sabenko from 1989, which I believe is actually one of the first papers on universal function approximation. At least for neural networks. Maybe this technology has existed for hundreds of years. I only know what I read, I suppose. So we're only going to have continuous functions, and that's pretty much what this is also going over. So let's talk about function representation with continuous mappings. So in order to do this, we're going to have to talk about Theorem 13. This is going to be one of the most important papers throughout the entire thing. So we're actually going to spend quite a bit of time proving this, but then we'll get to move on from function representation. So let's talk about representation. We want the exact function. We want decomposition that gives us the exact function we're looking for. So we're going to take some m and some n, which are members of the natural numbers, and we're going to require that m is greater than n. So because m, the size of the input set that we're using, we're going to create this function which maps r to the power of m, r with dimensionality m to the real numbers. And there's going to be functions which are not continuously sum decomposable via r with dimensionality n. You are going to need at least dimensionality m of your latent space in order to get a continuous sum decomposition of your target function. So let's talk about this. We can jump into Theorem 14. This is going to be m as a member of n. This is the exact same thing, but we use m instead of n. This is just saying you have the same dimensionality. Then f is guaranteed. F is guaranteed to be continuously sum decomposable via r with dimensionality m. Your latent space is big enough, therefore you can do it. You are guaranteed. For Theorem 15, we are just going to be talking about a variable set size. So if you have m elements, at most m elements in your subset, and the subset is along a line, and you have dimensionality of less than or equal to m, and all your functions are continuous and permutation variant, then you are good to go. So if your set has dimensionality at or below m, or if m is the latent space dimensionality, which is the size of your input set, then you're good to go. But if you go beneath that, it doesn't work. Now, how are we going to show that? Let's talk about the proof of Theorem 13, which is, well, showing that. So we're going to be talking about the max function. And the max function is going to be really funny because that is one of the functions that's extremely hard to represent. It's supposed to be really trivial to approximate. You know what? No, I'm not going to get ahead of myself. We are going to show that this, well, we're actually going to show it by contradiction. I'm going to show you two things that work, two things that should work at least, and show you that they can't actually work together. So let's go through this. Let's go through the lemma 16. So we're going to be talking about m and n, which are members of the natural numbers, and we're going to have some phi, which maps r to r with dimensionality n, and some rho, which goes dimensionality n back to r. And we are going to have our target function max, and we are going to have some decomposition of it. So recall some decomposition function. We're going to assume, wait, is this the lemma? No, this is the thing we're actually showing. So this should work. There's nothing saying that it shouldn't so far. So recall the latent space exact definition, and then remember that we're basically defining this right now because this is before the proof. The latent space of size m is injective for all m. Cool. So let's proceed by induction. For m equals 1, it's extremely clear. That's just saying that if you want one thing, you have one thing. Basically trivial. I'm glad we skip it. So we're going to have two sets. We're going to have two sets x. Come on, highlight it. There we go. Sets x and sets y. And we're going to have it such that their latent spaces are the same. So we can talk about set x as the set of maxes union added to the set of the remainder, and we do the exact same thing for y. So we're going to have x max is defined as the output of max x, and same for y. And now we're going to have these two. These two are going to be the same, and we're going to break these down into this little subspace thing that we have right up here. So as we look at this, we're going to have our phi of m minus 1, which is the remainder, plus the single thing, the single one that gets x max, the single input that is going to be x max. We're going to do the exact same thing for y. But the max of x and the max of y are the same. So these two right here, no, I don't want to highlight that much. This phi y max and phi x max, they are guaranteed to be the same because of this equation 6 right here. And of course, we defined that phi m phi mx and phi my, we defined them to be the same up here at the top left. So all that's left to say is that phi m minus 1 x rem and phi m minus 1 y rem is going to be the same. We're going to be able to say we're going to say that sentence I just said. So by the injectivity of phi m minus 1, which I assume that means injectivity into phi itself, we have the requirement, by definition of injectivity, that x remainder is equal to y remainder. And therefore, because the x maxes are the same by postulate, and, well, we defined them. Yeah, we defined them to be that way. And we have this right here the same. We have the requirement that x equals y. Therefore, it fits the definition that the latent space with dimensionality m, let's try going back. Latent space with dimensionality m is injective. We're good to go. All right, so let's move on. We did that. Now we prove Theorem 13. Theorem 13, if you remember, is saying that m needs to be equal to n. The two numbers, the two natural numbers, need to be equal to another, or n has to be higher in order to have universal function approximation. So we're going to proceed by contradiction, my favorite way. So functions phi and rho exist satisfying equation 5. So if we jump back to equation 5, just to look at it, we're going to have this max, which is the sum decomposition of max, and we're going to find our latent space m as r, with dimensionality m, the input dimensionality of the set, well, the dimensionality of the set, which is our input, is going to map to the latent space, which is going to be size r, the natural numbers, to dimensionality n, defining this. Well, we define this right now. So we're gonna introduce something new. We're gonna swap something in that shouldn't make a difference. We're gonna do something that shouldn't make a difference at all. What we're gonna do is we're gonna replace this rm input with rm ordered, and let all x, which are members, the set x, which are members of the real numbers with dimensionality m, we're gonna change those up so that it's just ordered. That's it. It's ascending. And we're going to let the ordered latent space be the restriction of the latent space to this just trivial bijection. Maybe it's not a trivial bijection, but I'm pretty sure it is. So all we're doing is saying, hey, latent space, you're going to follow the ordered set of numbers now. That way, we follow this set right here, this structure right here, to where we're always increasing. Should just be a permutation. Because this latent space of order, sub m of order, or whatever you call it, is a sum of continuous functions. It too is continuous, and by the thing we just showed, it's also injective. We're going to note that this R with dimensionality m, this ordered one, is a convex open subset. It's convex because up here we're ordered and we're always increasing. That fits the definition of convex. It's an open subset because we have some x1 and some xm. This is a finite set, and we're in a Euclidean space. So we're just going to imagine some number which is beneath x1 and some number which is above xm. If these are vectors, then we're just going to imagine some vector that's above or beneath them. And therefore, it's homeomorphic. Now, what are the requirements for being homeomorphic? F has to be a bijection, which is 1-to-1 and onto. Rm order and Rm should be the same dimensionality by the virtue of them having the same number, which represents the dimensionality. So there should be no problems here. So this should be homeomorphic. And oh wait, that's the first part. It has to be continuous. That's the second part, which we require from here on, from before. It's a requirement that we have on all functions that we're trying to represent or approximate. And F has to be an open mapping. Now, F is required to be an open mapping because we're moving from open mapping R with dimensionality M to open subset to the other open subset R with dimensionality M, but this time it's ordered. They're both open subsets. It's a function on those. Therefore, the function is required to be an open mapping. It should be homeomorphic. So our continuous function should be injective. We should be able to construct a continuous injection from our input dimensionality to our output dimensionality. But there's a problem here. There's a catch. No continuous injection should be able to exist whenever we're trying to use this homeomorphism from the thing we defined earlier, from our equation, from our sum decomposition. There we go, equation 5. From the equation 5 that I just showed you, the sum decomposition, it can't exist, even though there should be a homeomorphism between these things that we defined. It should work, but it doesn't. We have a contradiction. The sum decomposition cannot exist. So we are required to have m is at least equal to n in order to have a continuous injection. Otherwise, it just can't exist. So implications and limitations, it talks about how basically you don't need m, but you only need dimensionality m if you want the guarantee. There's going to be a lot of functions out there where you only need a latent space of dimensionality 1. And you just have to find out, kind of by trial and error, what your problem needs. The guarantee does not mean that that's just the situation that you should plug in. That only guarantees that it exists in some way. And that doesn't even mean you're going to find it. Because it exists doesn't mean you're guaranteed to find it. So that's a few things here. It just goes over to show that mathematical frameworks and engineering attempts in machine learning they're just not the same. So we can move on. So we can talk about universal function approximation. So we showed that for representation, we need at least dimensionality m in order to work. But what about approximation? What can we say about that? So we can talk about that, and it says it's going to be an analog of Theorem 13, and we're going to ask ourselves about universal approximation, and we're going to find out, spoilers, sorry, that m dimensions are still required. Whether it's representation or approximation, you need a latent space, at least the size of your set, assuming that your set is a cardinal set, of course. You need dimensionality of at least the set in order to guarantee that you can map that function, in order to guarantee that you can approximate or represent that function. Alright, so let's talk about universal function approximation with deep sets. So the first thing we're going to do is we are going to talk about the maximum error. How we're going to talk about the maximum error is by taking a prescribed phi and rho, and we are just going to plug them in, and they're created in such a way that it's easy to find out exactly what your maximum error is. Your maximum error is going to be log m over a. So with that, we can start to talk about some just basic definitions. For approximation, we define it as in a within epsilon approximation. We apply pretty much classical loss to it, what we get versus what we expect to get, and if it's within epsilon, you are, you're good to go. That means you are within epsilon. We are going to define this a as in log m over epsilon, where epsilon is our desired error, and m, of course, is the m that we've been talking about this whole time, the dimensionality of the set. So definition 18 is essentially going to be saying that in machine learning you learn, and as you learn you get better and better at what you do. Or right here, put more loosely, we're going to have some k, which is going to increase. K is going to be a member of the natural numbers. There we go. K is a member of the natural numbers. And as you increase your K, you get ever closer approximations to F. There's going to be some critical K, where K is also a member of the natural numbers, where as soon as you hit capital K, this critical K, you are going to be within epsilon. Every little k above that, which is not critical, is also going to be within epsilon, because we're assuming that you get better and better and better, and you never, ever, ever get worse. So, as we move on, we are going to have Theorem 19. Theorem 19 is going to be pretty much the most important one through this entire paper. We're gonna be talking about Theorem 19 for a minute. So, what is Theorem 19 talking about? There are a few more restrictions that we need to put down. So, of course, m is still going to be greater than n. We can generally assume for the rest of the paper that it's greater than it by 1, that m is going to be 3 and n is going to be 2. We are going to be putting out a couple of examples to where that's the case, strictly for visualization, although it's technically, for the theorem, all we're going to prove is that as long as you have n is less than m, you're not guaranteed a universal function approximation. So we're going to define a hypercube. A hypercube, of course, is a cube, usually a unit cube, going 0 to 1, but here it's going negative 1 to 1. It's going to have dimensionality m, and we're going to name it I sub m. It is going to be a subset of the the real numbers with dimensionality m. Then there's going to exist a continuous permutation invariant function f, which has no continuous approximate sum decomposition via r sub n. You cannot represent it if you have one less than the dimensionality of the set. So this proof is actually going to be stronger. We are going to have just your basic function. You have your worst case error if you just try to make some f with a constant function f of u is equal to this. That's great and all. But let's get into the important thing. So we are going to create this this function here. This is gonna be a really strange function. And it even says this definition may look a little arbitrary, but we'll talk about it later. It looks crazy now, but I promise it'll make sense later. So you're just gonna have to trust me, just like well, this paper asks for trust as well. So let's talk about what f star actually does. It's gonna be a sort. And sort is going to be a descending sort. That doesn't make a difference for the rest of the paper, but there it is. I was forced to read it, now you are too. So it's going to have this WT right here. This WT is going to be, of course the T is a transpose. I think that's a T for transpose, but that might be a perpendicular symbol. I actually don't know, but it doesn't make a difference. So what it's going to be doing is it's going to be taking the index of what you're putting in, and it's either going to make it -1 or +1. So you're going to have this really weird thing to where you're going to have, it's going to be biggest on the edges. So if we pretend like this line is going to be our set, we're going to have really big things at the edges, and it's going to get smaller as time goes on. And here's really big at the edges, and it's going to get smaller. So in the middle, it's the smallest. However, at the edges, it's the biggest, and it keeps jumping. It goes here, then it goes all the way to the other side here, then left, right, left, right, left, right, and it moves inwards until you get to the center. So let's get rid of those. There we go. And we can leave that. That's fine. So there's also going to be this beta here. This beta is literally just to keep it inside the bounds of the positive one, to make sure it goes from like 0 to 1 or something like that, or -1 to 1. I don't quite remember, but it doesn't really matter. Oh, you know what? Let's scroll down to where it talks about it. X or -1 is to ensure that f is bounded between -1 and 1. Now we know. Look at that. Isn't that wonderful? So the beta here, that's just a b. The b we can just ignore. That's really not important for the rest of the paper. But this function is going to be important because you need a latent space of dimensionality m in order to represent this, or in order to approximate this. We're done with representing. We're never going to talk about that again. So if we want to do that, we need to, let's prove the necessity for universal approximation. I'll bring this back up every now and again whenever it calls on equation 10, just because it's good to see it. But equation 10, our f star, is always going to be our sorting function. So we're going to do something really funny. We're going to do something really weird. We're going to talk about f, which maps this hypercube. It's not even a hypercube. Right now it's just a normal cube. We're doing this for visualization. We're taking m equals 3 and n equals 2. And we're showing that n equals 2 will not suffice. So with this f, this cube, we are going to think, it says here, we don't need to consider the whole cube. Since f is permutationally invariant, since it doesn't matter what order we funnel the set into the function, it's fully determined by its behavior on a set of points with descending order coordinates. And we're going to describe this as a simplex. Now, a simplex is a really weird thing. Let's pull that up real quick. And just in case you haven't heard of this, here is what a simplex is. Just for a couple of examples, what we're going to run into: a 0 simplex is a point, a 1 simplex is a line segment, 2 is a triangle, and 3 is a tetrahedron. Here is a really good... Oh, that's horrible. That's also horrible. That's better. This is a really good image. We're going to be dealing with this tetrahedron and mapping it to this lower dimensional thing, this triangle right here. But you also have the line, and you also have the point. And that's just great. We love that. So we're going to define this n simplex as x as a member of the natural number, the real numbers. That keeps tripping me up. R stands for real. R does not stand for natural. And it's just going to be descending. It's going to go from 1 to -1. And there's going to be n things inside of this n simplex. We're also going to have to remember the 2 extra, the 1 and the -1, but that actually doesn't come up a whole lot. But it is important to remember. This is going to be the heart of everything that we're doing, but I'm going to scroll down and explain it with words and then come back to it and explain it with pictures. Hopefully, explaining it with words will make it vaguely clear. You'll remember a couple of things, but the image... I think the image really shows what it's doing. So we are going to pick some phi, which sends it to a semicircle. The semicircle is strictly for visualization. This entire thing is strictly for visualization. We're going to prove that this is generally the case, but this example is really just designed to show you what the problem is, and then, well, let's show you what the problem is. So we're going to see there's going to be 2 solid red lines which intersect under applications of the latent space. But f star is going to be really good, and it's going to send them to opposite ends of the interval on the line. Let's show this real quick. And oh, I don't like that. It's almost good enough. So we're going to have this tetrahedron here, our 3 simplex, which our function is deterministically mapped out inside of. So our function, f star, it's going to be able to take these red lines here. Do you see at the top left, these red lines? It's going to take them and map them out to separate sides entirely. There's also going to be these dotted blue lines. These are going to be at the bottom right. You can see is that blue? That's close enough to blue. You can see these dotted lines are at the bottom right, and they are not too interesting for us right now. The interesting thing is looking at these red lines, which are not touching in any way, but whenever you look at their image under the latent space, suddenly there's an intersection here. That intersection is going to be a problem, because we're going to pass them into that, and our decoder is going to be asked to look at this spot, to look at this singular point, and be able to tell us which function does this one belong to. At best, it can choose one of the 2. It can't choose both. That is not a function, so it is going to fail. Some decomposition is going to fail under this example, because the function is able to map it out literally at opposite possible ends, but the latent space is not able to separate these out. The intersection means that it's going to fail. The intersection is going to be an extremely important thing in showing us that you have to have dimensionality m, and anything underneath that will not work. So let's go down. We're going to prove this in the general case. So as we see, this is going to be an n simplex, so we have a tetrahedron. We are going to be able to map it. I could have sworn there was something that it said that was interesting here. Here's where it's saying there's worst case error of at least 1. Well, look at that. So what we're going to be doing is we're going to be doing something very strange. So we're going to be taking that M simplex that we just had, and what we're going to do is we're going to make these two really weird sets. So here's two really weird sets, and we're going to have one to where 1 is equal to x1, and then we're going to have one to where it is greater than or equal to x1, but x1 is going to be equal to x2. And then we're going to do kind of a zigzag thing to where it jumps. It's going to be the first one is equal to, then it's less than or equal to, then it's equal to, then it's less than or equal to. But this one is completely swapped. It's swapped 1 over. This one is less than or equal to, and then equal to. This is going to be really strange, but the function that we just showed, let's see, this function 10 that we have right here is going to be able to separate out these two functions right here. However, the latent space is going to fail because we're going to have intersections just like we showed up top. So, it shows that based on the index and based on the -1 not being equal, you can know whether M is even or not. And okay, here we go, claim 20. This is the interesting thing. This is the thing I just said. F is able to separate these two. It literally just maps them to 1 or -1. Super straightforward. But phi cannot separate these two. For any continuous phi, which does this, there's going to be an intersection which is non-empty. So we're going to need to show this. In showing this, it's going to take 2 parts to show this. We're going to want to construct a gamma sub n which has a 0 only if the latent spaces have an intersection that is non-empty. And then, after we show that it's going to be 0 if there's an intersection that's not empty, we're going to show that it does have a 0. So, the main idea, it's super straightforward. We are just going to subtract the latent spaces. Whenever you subtract them, if there's an intersection, it'll be 0, right? And then, whenever that's 0, then you just make your gamma 0. It's not a row. I thought this was a row for the longest time, because what does it look like? It looks like an R, I know. So we are going to be dealing with the idea, oh, yes, the subscript is on gamma instead of n because it's going to have n, which is m-1 degrees of freedom, inside of these two sets. We can see this by thinking about m is equal to 1, where if they're the same, they're the same. If they're not the same, they're not the same. It's 0 degrees of freedom. So what we can do is, let's jump into lemma 21. Lemma 21, it already said lemma 21 up here. We are going to be constructing our gamma sub n. So we are going to, well, here's the answer. We have the proof just beneath it. So what we're going to be doing is creating this phi, which maps this line segment to the real numbers with dimensionality n, and we're just going to be defining -1 to be 0. This just makes the equations play a little bit nicer together. Then we're going to have some mapping gamma n, which maps the n simplex to the real numbers with dimensionality n by this function here. This function, just like equation 10, this one looks a little bit strange. It really does. But let's talk about what it does. Based on the index, your function is going to be either positive or negative. And from there, we're just going to be taking the phi's and inputting it, just like regular Genoese pooling. We're going to be aggregating this, and then at the very end, we're going to sum this very strange phi 1 over 2. But why are we doing that? Well, let's take a look at it. However, before we do that, there's more to this lemma. So we're going to suppose that this gamma sub n has a 0 in the n simplex. Then there exists some x plus, which is members of the top set, and x minus, which is a member of the bottom set, with the latent spaces being the same. If there is a 0 in gamma, the latent spaces are the same. So let's prove it. We're going to have some set z, and this z is going to be our, it's our intersection, that's what it's called, that's right. So z is going to be a member of our n simplex, and gamma n applied to z is going to be 0, because z has an intersecting, well, it's going to be an intersection point, just like we saw above. So we're going to define these things that we just said here, but we're going to define them in such a way that z sub I, if I is even, if the index is even, we're going to have x plus. And if it's negative, then we're going to have odd. Well, I said that strangely, but you can clearly see what it says. It's very straightforward. So, what we're going to do is we're just going to blindly plug them in. And so, let's take a look at them real quick. So, we're going to have, that's the wrong one. That's the right one. There we go. So, we're going to have this right here. If we look, it says there's going to be 2 of them. But if we look, it's going to have 2 of them because every other one is equal to the last. Or the next, depending on how you look at it. But one of them is going to have this phi 1 right here, this phi 1. The other one is going to have phi of negative 1, but phi of negative 1 is 0. So, if we only, I think we're done looking at this for now. If we only look at the x plus, we can define the latent space completely for x plus by this function right here. And we can also do the exact same thing for phi minus. So, this is what we want. Then we need to show that these 2 things are equal. We're going to do that by redefining this in terms of z sub I. So, here it is in terms of z sub I, whenever these 2 things are equal, based on the indexes. Do you see how the indexes here were for the equals, but here it's for what we define z to be? So, all we need to do now is just plug in our x minus and our x plus, and suddenly, if all we do is we take the left-hand side and subtract it from both sides, we get a 0 where we're adding together both latent spaces, which can give us our gamma. And we've definitively shown the case of intersection of the set Z which intersects, that the phi, the latent space, are going to be the same. So we've shown that there is a valid gamma with the form, right here, with this form of equation 14, that has a 0 whenever there's an intersection. And all that remains is to show that gamma sub n has a 0. Now, this is going to be a little bit more involved, but not very much more. The one above took one function, but this one's actually going to take 2 others besides this gamma. So we're going to do something kind of weird. We're going to do something kind of strange. We're only going to talk about the behavior of gamma sub n on the surface of this n simplex. And of course, each face of the surface is itself a simplex. This, I don't like this sentence. This is a really confusing sentence. What they should have, I say what they should have done. It's a well-written paper. I enjoy it. But what I would have written personally is saying that whenever you have a tetrahedron, whenever you go one dimension beneath, you get a triangle whenever you're talking about the surface. This is a very straightforward thing. This sentence, it tripped me up. That's why I'm kind of over-explaining it a little bit, that each face of the surface is itself a simplex. So all we're doing is we're saying that the surface of a tetrahedron is made of triangles because simplexes have flat surfaces. So there we go. So the simplex of the surface is going to be of dimension n minus 1, and it's going to be defined by changing one of the inequalities in equation 11. Now you may be asking, what is equation 11? Well, I asked that at least, and that's going to be this one right here, this n simplex, and it's just the descending one to per 1, then x, 2, 3, 4, that we defined the f on, that we said the f is completely constrained on. So we are just going to apply the constraint that one of the x sub I is equal to the next one. And we're going to talk about these surfaces with 1 to n. We're going to talk about them as this right here. Now, do you see this is going to be a 4 simplex, but we're talking about the first surface on this 4 simplex. Here we have the second one, the second face, and then the third face. So if we look, the first face literally has x1 is equal to x2. Then for the second face, we have x2 is equal to x3. And then for the third face, we're going to have x3 is equal to x4. And that's it. That's all we're doing. But we're going to get to the interesting part, the really, really important part. There's 2 more faces to consider, the 0th face and the nth face. There's going to be a relationship. And that relationship, we're going to call it the coordinate left shift in point of the n simplex on the 0th face to a point on it. And the output is literally just this gamma sub n multiplied by -1. We are making gamma negative. That seems really useless, but you're going to see that's super important. This coordinate left shift is the bijection named alpha, and is going to map from the 0th face. Strictly, input is the 0th face, and the output is the nth face. It's going to be that mapping, and it's defined like this. We're going to have this alpha of the set x sub I, and we are going to be talking about x sub I plus 1 if, if you haven't reached the end, it's just going to be the next one. But if you've reached the end, just slap a -1 in there. So let's take a look at what this means. Let's look at the 0th face and look at this example right here on the 4 simplex. So we have 1, 2/3, 0, and a -1/2. And we're going to be applying alpha to it. And we have 2/3 here. So here's 2/3. We're going to be on the opposite, of course. This is going to be a right shift, but here we see a left shift, as we do. So this 2/3 is going to move to the left. And then the 0 is going to move to the left, and the -1/2 is going to move to the left. Do you see? So we are going to ignore this 1, because that's going to just go away. That's going to be too far left to see. So we're going to have 2/3, 0, -1/2. And here we have 2/3, 0, -1/2. Then we get to the case to where I is equal to n, so we just literally slap a -1 in there. And suddenly, not only have we made gamma negative, the important part, but we're also on another face of the simplex. So now we're going to apply this, and we're just going to go through the motions. This is actually just showing the output, and we're seeing that this gamma turns into a negative gamma whenever you apply this. And here it is written again. Whenever you apply alpha x, you are going to get negative gamma x. The alpha just makes it a negative. And this is going to be the most important thing, because we can exploit the symmetry to show gamma sub n has a 0. So in order to show that we have a 0, we're going to need the Porsugalam Theorem. So let's talk about a little bit what that is. Well, I say let's talk a little bit. It's written completely right here. If we can fit this form, then we are guaranteed to have some intersection such that the function on the intersection is 0. So this is going to be extremely similar to what we've been doing before. We're going to have the hypercube of dimensionality n, the unit n cube, even though technically I've only seen the unit n cube going from 0 to 1. It kind of does trip me up. We are going to be taking del I sub n to be the surface of this hypercube, to where we define it right here. Del I sub n is going to be defined as x is the set of things inside of this hypercube, where some dimension inside of that is either plus or minus 1, for some I, as it says right here. And we're going to have this f. And this f is going to be a mapping from the cube to the real numbers of dimensionality n. It's going to be continuous, and for every x sub I, we're going to have this thing here. This is the heart of the Porsugalam Theorem. This f of negative x means we just pull out this negative as if it's just a constant, as if we have a linear function, and have this negative right here to show for it. Then there's some intersection point inside of this cube such that the function is 0. That if we can prove that, we have fundamentally proved that you cannot have dimensionality m of the latent space, or dimensionality of the latent space being less than m. This is the last part. However, there's one last thing that we need to do. It says right here we can see a clear similarity between these two things. It's this 19 right here and this 20. These two functions, but we cannot directly apply this Porsugalam theorem to gamma sub n. So in order to do that, we're going to need what is essentially a kind of weird change of coordinates, which maps I sub n. It maps this cube to the n simplex, which turns a negation into a left shift. It's going to have to require those two things. Well, let me show you right here. It's going to have to require that gamma on x, if you apply it, that is x. That gamma on negative x is just alpha applied to gamma sub n of x. If we can do that, then we can fit our f of x is equal to negative f of x in terms of our gamma. We are going to be able to get a negative gamma, and this x is going to become positive. Do you see? That is going to be fundamentally well, I say fundamentally, that was an unnecessary use of the word, but that is going to be the last piece of the puzzle that we need in order to complete the proof. So let's talk about this. Let's do this exactly like we did before. I'm going to scroll down and talk about the words real quick, and then we're going to come back and show the image, because I think the image really shows what we're trying to do here. But you just kind of have to stare at it for a second. Just like all good images, all good artwork deserves a fair glance, a fair bit of time. So let's talk about lemma 23. N is going to be a member of the natural numbers, and gamma sub n is going to be defined as in equation 14. What was equation 14, you might be asking? Well, equation 14 is the only way we've ever defined gamma. So that's pretty straightforward. So there exists a continuous function, nu sub n, such that it maps this hypercube to the n simplex, such that for x on the surface of this hypercube, we're going to have this thing right here, which fits the Porsugalam Theorem. So we're going to present a partial proof. We're going to be showing all the important bits. There's a few loose threads you have to take care of once you're done with it. We are not going to concern ourselves with those loose threads. We are just going to assume that everything falls in line. So strategy is not quite as simple as suggested above, blah, blah, blah. So let's see. We are going to be defining two faces. If you remember, our alpha was only defined on two faces, so we're going to make something extremely similar here. We're going to have the top face of this hypercube and the bottom face of this hypercube. It's not a hypercube anymore. I don't know why I keep saying that. This is a visualization. There are explicitly 3 dimensions. This is a regular old cube. So these I plus n and I minus n are going to be naturally equivalent to just dropping the dimensionality down of this cube. We're going from a cube to a square, or 2 squares here. And we can do that by dropping the last coordinate of x. So we're going to define this any point whenever we just drop the box down by dimensionality 1 as x bar. That is, x bar is x with the last coordinate removed. Do you see? To where, let's spoil a little bit to where we're going to have this x right here, or this y right here, and x bar is literally just dropping off this, I think before we defined it as z. Let's keep this dimension as z, this vertical dimension as z. We're just dropping the z dimension, that's it. We're just throwing it away, and then we get our y bar and our x bar. And so we're going to remember that that is a part of the square that was built by the cube. So we're also going to have the 0th face of our n simplex and the nth face of our n simplex, which is where we defined alpha to be. These are naturally equivalent to dropping the simplex down by 1 dimension, just a general triangle, to any point on x as a member of the 0th face of the n simplex. And we can define these as prime is going to be in the simplex. This bar is going to be on the hypercube, or this lower dimensional cube, the square. X prime is going to be in our simplex. So if we just say 1 x prime, then we're good to go. We're back on this this n simplex of the face n or 0. So that's how we're going to build this. We're going to have this x prime and this x bar that we're going to use to build nu sub n, where nu sub m is written in terms of nu sub n minus 1. Now, this was a lot of words, so let's just show you the equation. I feel like that'll actually clear things up a lot right now. So we're going to have it here. This nu sub n of x is defined in terms of nu sub n minus 1. But on the top face, that's going to be similar to our n simplex on the 0th face, where the input for our alpha. But we're also going to have to be dealing with this I minus. So we're just going to have to translate it a little bit so that it feels, for the functions, it always seems like the input is going to be in this plus, and it seems like for the input, we're always going to be dealing with the n simplex of the 0th dimension. Yeah, see, right here. We are mapping I plus to n simplex of 0, the 0th face, using this, right here. So we define it carefully. We literally just slap a 1 if it's the 0th face, and we slap a negative 1 if it's the nth face, and we have this alpha right here to travel from the language of the 0th face to the nth face. And then we're going to be able to input our x bar to where we're talking in terms of the square, but the output is going to be in terms of the simplex. This is going to be super important because we're going to need the output to be in terms of the simplex. So that's going to be that, and we consider a point lying on, oh, this is getting into the verticals. So I think it's time to go back up here. We are going to explain this. So we're going to talk about nu, and nu is mapping. Here is I2 to the 2 simplex. So we're mapping from this square to the 2 simplex. Or if we move a little over to the right, we're mapping, here's our nu 3. Nu 3 maps a cube to the 3 simplex, to our tetrahedron, as we saw earlier. And there's going to be some mapping up here on the cube itself. We're going to have x and we're going to have negative x. But the only relationship they share was going to be through this alpha. This alpha was not good enough. It did not work. So we have to use this nu in order to create this 3 simplex on the 0th face, which is similar to dropping this dimensionality down by 1, which is going to be our n minus 1 simplex. And from here, whenever we map it out, nu 3 of x and nu 3 of minus x are going to be related through this alpha. And of course, we can see the nth face, where n is equal to 3 here, is going to be similar to a triangle, which is the face of a tetrahedron, of course. And we're going to be able to have that. And that is going to be the whole thing of what we're doing. Do you see how this is essentially just a really weird coordinate change? Exactly like we did to our function f way earlier, whenever we just said we don't actually need the function of f. We only need a descending ordered simplex representation of the function itself. So, from there, we can get on to the case that it is not on those 2 surfaces. I've never seen this notation before, but here it is. So this del I sub n, meaning we're dealing with the surfaces, but this slash right here means not in terms of sets. I've never seen that before. I've only seen sets that like have the epsilon, which means like included in, just crossed out. Usually crossing out means not, but here this division symbol means not. I'm using words too much. So what we're talking about here is the union of the plus face and the minus face. Ignore those, throw those out, but talk about everything else on the surface. What we're talking about here are things like x and y right here. These 2 are not on the top or the bottom surface. They're on some vertical, on this vertical line, and they're going to be in between them. They're going to be on 2 different faces. And here's what we're going to do. Its beauty is in its simplicity. All that information of being on a different face, just throw it away. Just take it and chop it off. Literally just give it a constant value. We don't care. Just throw it away. And then there's nothing stopping you from mapping y bar right here into this negative x, fulfilling everything that we're looking for. So in the case, we're going to talk about those surface verticals, where that's just the vertical dotted lines that it was lying on. Throw everything else away and ignore the rest. And now, the only thing to show is that this y right here and this x right here, these 2, they are going to be negatives. If we can show that, we have completed everything that we need, and we have shown that nu is a valid function that fulfills our purposes. Oh, and so we consider a pair of antipodal points, x and y, and these are not going to be on the surfaces we already defined everything to be on. So x plus and y minus are also antipodal. X plus and y minus, we're just going to talk about this in terms of functions real quick. So we're saying that y is equal to negative x. So if we did this right, this y minus should equal x positive, because these 2 are basically opposites of each other, as we see right here in point 16. So all we need to do is show this, and we are good to go. Let's see, it's constant on surface verticals. So we can just say that the gamma n, using nu n of x plus, is equal to this. We're just giving it constant values, and we can just slap in the x plus and the y minus here. So we have that these 2 things are going to be equal to each other if we ignore this negative right here. So we have this relationship here, this x plus and this y minus, which is just literally mapped out to x and y. And now we are just going to plug it through the functions that we have already defined. We are going to blow through it, and we're going to find out that, surprise, surprise, the proof is right. God, imagine a math paper that like the proof just ends up being wrong. Like that'd be weird. Of course the proof is going to be right. So we have some x plus and we have some x bar, where x plus is going to be a higher dimension than this x bar, which is why we also see this 1 here. We've just broken it down in terms of how we've defined our new. Did I actually grab that? No, I didn't. Okay, it's actually not so important, because I'm sure you just remember, or maybe I can just scroll up to it, yeah, here it is right here. So this is how we defined our new right here, and we just follow that function. We plug everything in. As we plug that in, we find out that we get this, we're actually just going through what gamma actually does. So we're going to get this 1 right here into this -1, because okay, let's pull up our gamma real quick to show why that's -1. The first index is just going to be multiplied by -1, so we get that. And then we're going to have this thing here, which is literally just plugging in the gamma, and then this right here from, well, it's all from gamma. You're just going to have to take my word for it. And you get this negative gamma n sub n minus 1 of nu sub n minus 1 on x bar. And so we can do that. That was for x plus. We do the exact same thing for the minus, and we get this, which is going to be the same thing, but instead of negative gamma, we're going to get negative x bar. So we can, let's see, x is a member of that, and as we plug it through, we are going to find this, that they are the same. They are exactly the same. Isn't that a beautiful thing? The negative right here and the negative right here, they just die. And so we see that it takes on the same value at the other end of each surface vertical. So basically you're just reversing. So it remains to extend that nu sub n, so, well, that's it. Showing this was the last piece of the puzzle. It shows that nu sub n is a valid function. Do you see what this means? This means that our gamma is a valid function, and the gamma's whole point was to show that there was an intersection. Do you remember so long ago, whenever we were showing, let's scroll all the way back up to it. Feels like a lifetime ago. We were talking about the intersection of these 2 points because we dropped down 1 dimension. That does not fly. That is not allowed. You need dimensionality of m in order to be able to do this. And there we go. So we're done. We did it. Theorem 19 is complete. We have proven that for either function representation or function approximation, you need a latent space of at least size m to guarantee what you're doing. So let's talk about what we just did. We briefly summarized the chain of reasoning. So we want a permutation invariant function to approximate. The input space is going to be some hypercube. We want to use some decomposition, and the dimension of the latent space n is 1 less than the input space m. If we create our encoding map of gamma, which maps this line segment to the real numbers with dimensionality n to the function gamma sub n, it's going to not only have a 0, but we are going to show, whenever you do this, whenever there's a 0, you're going to collide under the applications of the latent space. There's going to be that intersection we talked about, and the decoder's not going to know what to do with it. So it is impossible to approximate by some decomposition because of that collision, because of that failure. There will always be a pair of points which collide under the sum decomposition if you require that latent space. Of course, this is going to be exactly like representation. There's no guarantee that you need m for every single function. There are going to be some functions which you only need a latent space of size 1. Some functions just don't need that much. We go into the visual intuition. I'm going to be honest, this I feel like didn't help me so much, but I'll go through it. Basically what they're saying is, we go back up. If we look here, there's going to be this, these are going to be contours of the max function. And as we look at the true max function, it's going to have these right, along the y equals x line, it's going to have these right edges. These 90-degree turns that it makes. And the functions, being continuous, are just not allowed to do this. As your k increases, as you get better and better at what you do, it will become sharper, but will never be perfectly sharp like the max. So you can approximate it, but you can never represent it. So it's very hard to represent, but somewhat easy to actually approximate. So let's see, what else was there? There was one other thing. Oh yeah, whenever it's talking about our f star, our sort function, if we look at the contours of that, they're always going to be just these y equals x lines. These y equals x lines, Theorem 19 violates this badly, having a contour along y equals x. and perpendicular to the contours of any sum decomposition. It's basically saying that f star is extremely hard to represent because, well, by visualization, looking at these contours, they're extremely hard to represent. So that's the reason why it failed, and that's the reason why you need least dimensionality m. That was the heart and soul of the paper. That was the whole point. We're going to talk about some other things that are interesting right now. So we're going to talk about sorting. The idea behind sorting is literally just talking about that permutation and variance. What if we took permutation and variance and how we made our functions permutationally invariant and just took that out? Our sum decompositions, what if that was independent of what we'd use to make the set permutation invariant? So it talks about taking sorting and just making it, learning a canonical way to sort them before feeding it into permutation-sensitive networks in order to make a permutation invariant output. It's just saying, what if we had another neural network to take care of one of the jobs, instead of having this end-to-end thing? Seems great, but well, that's it. It seems great. So another thing is going to be the relationship between deep sets and graph networks, because of course a set can be seen as a graph that's only composed of nodes, of no edges. How you actually put those edges in is going to be a really interesting question that hopefully somebody's going to answer. Of course, we can also look at, oh yeah, I was going to bring it up. This wasn't really brought up in the paper, but it reminded me of it. Right here, if we actually look at the attention is all you need paper, we can see that down here at the very bottom is just the positional encoding that you actually use. This reminded me of it because it's asking, how do you actually use this positional encoding if you have a bunch of nodes? In a sentence, of course, there is an outright position that you can make. But the question was like, oh, what is the positional encoding? It made me think, oh, well, that's an active area of research for transformers, you know, how you actually create this positional encoding so that your transformer can learn exactly how to maneuver within what you're doing. Positional encoding is absolutely a hot topic right now. So there's that. There's approximate permutation and variance, which is very much like K-area Chinosi pooling. There we go. Chinosi pooling, very much like K-area Chinosi pooling, to where we only take a subset. So we are going to write a T sub k of x for the set of all k tuples of coordinates x. Oh, wait a minute, no, I've gone too far. This is saying, what if we increase from deep sets, which is k equals 1 to k equals 2? No, for sets to graphs, approximate permutation and variance is just asking, hey, what if we don't use the whole thing? Let's just chop it off and be approximate. For Chinosi pooling, it's an open question of like actually how much you need. Let's take a look at this image real quick. So we spent the entire thing, this entire paper has been on k equals 1. However, we showed that you need at least dimensionality m in order to guarantee universal function approximation or representation. But for the minimum necessity, it seems like if you have k equals 2, it might take a while, but if your latent dimension is 1, you should be able to just hard encode every single relationship in the set into what you're doing. Of course, with maximum sufficiency, they say, well, let's be safe and just plug m in until you get k is equal to m, and you're just plugging the whole set into each singular phi. So as we look at this, the purple is the question mark region. The purple is saying we don't really know what we need. Here's the A is the minimum of what we know that you need. You know, here's the bare minimum in order to guarantee these things, and the maximum is saying, well, here's absolutely what you have in order to make sure that you don't miss it. But there's a lot of questions here. There's a lot of the smaller purple circles show possible true, necessary, and sufficient conditions for universal function representation. It's an open area of research that could be looked into. Some other open questions are K-area Chinosi pooling, if we change that, and a couple of other things. Oh, we get back into sorting. I just really think that we have pretty much finished everything. Yeah, here's the conclusion. We did it. We focused on deep sets the whole time, and we proved exactly what dimensionality you need for representation and approximation. Yeah. Cool. So then we get on and we get into the last section, which I'm just not going to be going over the appendix. It is, I read through it, I tried to understand it, but let me tell you, including it into a YouTube video would be, I think, difficult. And that has been the paper of universal function approximation via oversets. I hope you've enjoyed it, and have a good day.